Imagine a network of autonomous agents working together. In every round of interaction, an agent has to make a single routing decision. It must choose exactly one peer to consult for help. Two variables make this difficult. First, peer capabilities are latent. You do not know who is good at a specific task until you test them. Second, they are non-stationary. The peers are adaptive agents themselves, meaning their responses evolve as they learn. Faced with these hidden, moving targets, large language model agents fail to explore. They lock onto an early favorite in the first few rounds and persist in querying that single peer, regardless of whether that peer's answers are correct. We see this behavior even in frontier models. Out of 297 interactions, GPT-5 queries a single Qwen 7b node 294 times, ignoring the rest of the network almost entirely. The observation that a model like GPT-5 exhibits the same routing collapse as its predecessors suggests that exploration might be a structural hurdle rather than a simple matter of model capacity. When an LLM fails to execute a behavior, the standard developer reflex is to prompt it. In this case, you provide the model with its full interaction history and explicitly instruct it to balance exploration and exploitation. This in-context exploration approach actually degrades routing performance. To measure that degradation, we can compare the prompted model against a naive random baseline, a policy that simply rolls a die to pick a peer. This chart tracks the cumulative regret offset. The zero line represents random chance. Under contextual diversity, the prompted LLM's error rate crosses decisively above zero. Providing perfect context and explicit instructions results in routing decisions mathematically worse than a die roll. You cannot prompt your way out of this problem. You must impose algorithmic structure. To build that structure, we first formalize the entire multi-agent network as a partially observable stochastic game, or POSG. This is computationally categorized as NEXP hard. Finding an exact solution for a finite horizon POSG with adaptive peers is intractable. It requires jointly modeling the exact evolving state of every agent simultaneously. The MACE framework circumvents this. It shatters the joint POSG down into n independent contextual bandits. This decomposition trades intractability for a new challenge. In a standard bandit algorithm, the arms you pull are stationary. Here, the arms are non-stationary agents, meaning our algorithm has to capture their evolving utility at every step. By sacrificing the impossible task of joint network awareness for independent, localized bandit algorithms, we make peer routing mathematically tractable. Traditional bandit algorithms rely on scalar pull counts. They track how often a peer is used, but remain entirely blind to the context of when they were used. For adaptive peers, a simple count fails. MACE translates that complex agent interaction into a relational feature vector, expanding the scalar state into 4 distinct channels. Response diversity measures how much a peer's answer diverges from your own, serving as a proxy for potential information gain. Peer distinctiveness measures distance from the rest of the network to identify specialists. Historical performance provides a peer exploitation signal based on empirical success. Interaction round modulates how aggressive exploration should be as time advances.
With these 4 dimensions, the system can distinguish between a peer that is undertested globally and one that is undertested in this specific relational context. This relational vector feeds into the LIN-UCB selection equation, the engine that calculates the score for every peer, every round. The left side of the equation is the ridge estimate. This represents exploitation, relying on the known data of a successful peer. The right side is the uncertainty bonus. This represents the exploration imperative, expanding to offset the weight of known data. The alpha scalar is the master knob. It inflates scores for peers with high relational uncertainty to mathematically force the system to test them. The LIN-UCB engine operates by prioritizing uncertainty. It mathematically incentivizes the agent to map unknown territory by treating a lack of historical data as a valuable asset. Once a peer is queried and a reward is calculated, the system updates its statistics in a feedback loop. This update is targeted. The uncertainty bonus shrinks only for the chosen peer, leaving the rest of the untested network highly incentivized for future rounds. We can test the necessity of this bonus by examining the failure boundary. If we set the alpha scalar to 0, we strip the uncertainty bonus out of the equation entirely. An alpha of 0 turns the algorithm into a purely greedy policy. Without the exploration incentive, the system immediately collapses into premature commitment. This greedy mathematical baseline is the exact structural twin of the LLM's natural failure state. The uncertainty bonus is the sole barrier between autonomous routing and complete network collapse. We can observe MACE applied against the in-context baseline, using datasets like HotPotQA and Math 500. The prompted in-context exploration model triggers a catastrophic selection collapse. Out of 1,500 selections, it funnels 1,297 to a single distractor peer. Conversely, MACE's selections are smoothly distributed across all 10 peers, displaying high network coverage and gathering real capability data. In an exploitation phase test, MACE's learned weights are frozen with no further updates. Even then, its performance gains transfer seamlessly to entirely unseen benchmarks. The stability of the results across new benchmarks, even with frozen weights, indicates that MACE identifies a generalizable structure for multi-agent interaction. The final variable dictating the value of exploration is capability diversity, denoted as delta. This measures how specialized the agents in a network are. We can map the stakes mathematically. Greedy, non-exploring agents incur a steep linear regret curve. MACE achieves a flattening sublinear regret. If we analyze a homogeneous state where delta is near 0, meaning all agents possess the same capabilities, the regret curves are nearly flat. Exploration barely impacts performance. But as agents develop unique, heterogeneous skills, the cost of greedy commitment skyrockets. The gap between the linear failure and the sublinear success widens immediately. Because peer capabilities naturally evolve and diverge over time, exploration is strictly non-optional for any advanced multi-agent system. A systemic routing limitation that trillions of parameters inside GPT-5 cannot overcome can be reliably addressed with 20 lines of ridge regression and a mathematical optimism bonus.